Welcome to Bowie State University's Data Science and Analytics Initiative, and the College of Business presents the Data Science Analytics Research Webinar Series. Today is the first of a two-part series on machine learning. Our presenters will be Dr. Azina Zeinabi and Mr. Jamar Smith. Dr. Azina Zeinabi is a full professor and chair of the Information Systems Department in the College of Business at Bowie State University. He is co-PI for the NSF Data Infusion Grant at Bowie State University as well. Dr. Zeinabi is an experienced practitioner and educator of information systems with over 20 years of experience that includes extensive work in systems analysis, design, and development. Dr. Zeinabi's research focuses on business intelligence and decision support using data mining and various data representation and inference methods, as well as cybersecurity threat analysis. Dr. Zeinabi has published in numerous publications, and he has garnered funding from the National Science Foundation, the Federal Cyber Scholarship for Service Program, and the Capacity Building Track. Our next presenter and guest to Bowie State University is Mr. Jamar Smith. He is Chief Technology Officer for The Public Block Incorporated, where he is currently leads the technical development and innovation of all technical products. Previously, he specialized in assisting data science teams and machine learning engineers with deploying machine learning models into enterprise production environments. His experience ranges in several industries, including healthcare, government, and financial services. Jamar has received his master's degree in science and information management and a certificate in advanced studies in information security management from Syracuse University. He also holds a bachelor's of science in statistics and a bachelor's in arts and Africana studies at the University of New Mexico in Albuquerque. Welcome to our presenters and welcome to our guests. Can you all hear me?
Yes, thank you.
Oh, great. Jamar, before we get started, I hope I can call you Jamar. Can you tell us a little bit about your company, Public Block?
Yeah, so just to give a high-level overview of what Public Block is we're a company that focuses on auditing, compliance, and transparency, particularly in the construction industry. So we have a suite of tools that allow people to be able to communicate with each other, from subcontractors and contractors all the way to the investors and project sponsors. And we utilize blockchain and machine learning technologies to be able to help facilitate that communication. And we also have a series of products that are currently in beta stage that are around that same theme of auditing and compliance and transparency, where we'll be looking at different industries and different use cases. But in a nutshell, that's what Public Block is.
Great, excellent. So the way we're going to start today is, Jamar, you're going to go through your slides, and Dr. Zeinabi, he's going to work with you, and you all are going to have a conversation. If you all have questions, please feel free to ask your questions, and I'll be here in the background in case you all need any technical support. So welcome.
All right, sounds good. Thank you.
All right, Jamar, before you start, I think for the participants, if you have any question, put your questions through the chat. Number two, there is two series. This is the first week. Next week is going to be more of a hands-on and practical part of this webinar is. So Jamar is going to take and start the presentation.
All right. Thank you, Dr. Zeinabi. So welcome, everyone. So as Dr. Zeinabi said, today is going to be the part one. And really what my goal is with this is really just to level set everyone with what machine learning is, as well as what the model creation looks like. So that's the main goal of today's. Next week, we'll do a short little deep dive on more the advanced part of machine learning with deep learning and neural nets. And then we'll go ahead and do more hands-on experience with the next session of actually going through and cleaning some data and building a model. And with that being said, what I want to share is I sort of have this broken up into two different presentations. And the first one's really this introduction to what machine learning is. And so this agenda for this first half is really going to be focused on the introduction of machine learning, the value of machine learning, and then the team development around machine learning. I think sometimes we forget that this IT phases tend to be a team sport, and it takes many different individuals with different skill sets to really make machine learning successful. Now, before I get going on machine learning, I have a poll that I just want to do very briefly to get a better understanding where everyone is with machine learning. So I'm going to go ahead and publish a poll. And really what I'm asking here is, what is your experience with machine learning? You know, are you new to machine learning? Do you have some, class knowledge, or you've been in a lecture with machine learning? And then have you built a model before? And then are you experienced with machine learning? So I have that poll up now. I'll give it probably about 30 seconds to see where people are. And it'll just give me a little bit better understanding where to focus the presentation. Okay, I think that's good right there. So I'm gonna go ahead and end the poll now. And from the results that I see, it seems that the vast majority are new to machine learning, have some knowledge, and then a few of you have some experience and have built a model before. So that's perfect. This is going to be right in line to where most everyone is in this presentation. And then as Dr. Zenebi said, go ahead and put your questions in the chat. And I do want to make this as conversational as possible. So as you ask questions, Dr. Zenebi will be pausing me, so that way I can go ahead and address those questions and answer the questions for everyone. So before we get going, I do want to just do a little bit of a deeper dive about myself, just to give you a little bit more background on my experience and what I've done before I came to Polyblock as the CTO. So I'm originally born and raised in beautiful South Central Los Angeles. After high school, I actually was a welder, and I welded for about 3.5 years. And 2008 happened, and it was really difficult to get work. So I decided to go back to school. Started off at a community college and wanted to be an engineer since I was in welding. From there, I transferred to the University of New Mexico, where I just fell into statistics and double majored in Africana Studies. And after that, I worked at the Cancer Center at the University of New Mexico, and I actually worked as a statistician in breast cancer research. So I focused primarily on health outcomes for women of color diagnosed with breast cancer, and then looking at analysis of policies in the hospital to see how we can better treat women that were diagnosed with breast cancer. From there, I went back to school to get my graduate degree. And then from there, I joined IBM, where I specialized much more on machine learning at scale. So building models for Fortune 500 companies, large government agencies, to do a lot of prediction around fraud, optimization, things like that. And then came over to Polyblock to start building out a platform from there. So as we get going, one of the things I just want to kind of put to the side, especially in the introductory about machine learning, is I want to put the buzzwords aside. There's a lot of different names, and to give you some context, the term machine learning has been around since I think 1956 or 1959. So it's not a new field by any means. What's become new in this field is the convergence of compute as well as the algorithm. So now we have the ability to utilize machine learning. And so I just want to set aside the buzzwords. It's, people call it data science, data mining, statistical modeling, machine learning. All of them have the same goal. And it's really, how do we get information from data? So how do we make better decisions as we move forward? So we'll go ahead and start with just a formal definition of what machine learning is. And the formal definition is, computers that learn without being explicitly programmed. And for anyone that has any experience with computer science or building programs, you know that there's a lot of logic that goes into building a program. So a lot of if-then statements, and you have to try to think of all of these different rules that need to take place. And something like a small application that does something simple as, entering data for the number of students that attended for the day. You could think about all the logic there. It's not too difficult, right? You can do, if a student absent, then mark them this way. If they're present, mark them that way, right? But as you get into these more complex use cases, for example, Amazon trying to optimize its operations with city packages. So they have thousands of trucks going to thousands of homes. There's almost an infinite amount of possibilities in how they can route these trucks to make it efficient for them to deliver packages. That's where machine learning comes into play, where it can learn from that data and really start to optimize. So this third part I have is you have data, and I really have these data points separated, and there's different volumes of data, there's different types of data. But the main objective is we're trying to get this data into a form where we can do some analysis. And really analysis is just learning from the historical trends or behavior within that data. And if we have a pattern within those historical trends or within that behavior, we can make some predictions and provide some insights moving forward with that data. To just give that a little bit more context, if we look at the type of data that we've had before, so I'll kind of stay with an example from the healthcare industry. Is a physician would have an MRI or an X-ray of a tumor, and they would really examine that image and really try to determine a lot of different characteristics of that. And before they would do a biopsy, they're really trying to make a determination, is this benign or malignant? So is it cancer or a non-cancerous growth? And that dictates how quick and how soon and what the process is for doing a biopsy and doing all the other procedures. So that takes a lot of knowledge, right? So a physician is going to have to go to school for many, many years and then have a lot of years of experience to be able to look at these images and start to make some predictions of their own based off of their historical patterns and experience. And so there's this data, there's this human input, and then there's an outcome. What machine learning does to help advance that is, instead of just that one physician's experiences, I could take experiences of a wide range of physicians looking at the same type of tumors and same cancer, same patients, and then be able to start to look at a historical pattern using machine learning and be able to do more analysis around that and give more of a augmented experience to that physician to say, okay, based off of what we know previously of different MRI images, we can determine that there's a high probability that this is malignant. And so we need to go ahead and do the processes for malignant growth. And then if it's benign, then let's go ahead and start the process for removal of benign tumors. So that's really just what machine learning is it just helps augment the decision process and takes experience, not just from someone's expertise, but it can gather a wide range of expertise, a wide range of data, and be able to learn from it.
Yeah, there is one, Jamar, there is one question.
Okay.
From Dr. Ntembe. What kind of data can we process with machine learning, structured or unstructured?
Yeah, so that's a good question. I'll definitely do a deeper dive into this throughout this presentation, but just to give a quick overview is we can process both, right? Structured data is just data that's in rows and columns and is pretty easy to navigate. And then unstructured data might be something like an image or text that we want to process. And there's different methodologies for both, but we can handle both in how we do that. So there's something called natural language processing where we do text. There's something called image analysis where we can do around images and that unstructured data as well.
Yeah, I just want to add that even if it is unstructured data, through that process, it will be converted to some kind of structured data before it's fed into the machine learning algorithm. Yeah.
So there's a process called vectorization that takes place on unstructured data. So eventually it all becomes structured for the computer reading. We just classify it as structured or unstructured from our point of view, but the computer will always put a structure around it. So now we have just that high level overview of what machine learning is. Let's really take a deep dive in what's involved in machine learning, and this will kind of set us up for the rest of the presentation of what is machine learning. And so what I'll do is I'll start on the left hand side where it says model. On the top side we'll do the machine learning prep, and then we're going to go in a circle around this clockwise. So machine learning prep is really the first step is having a clearly defined business problem or problem that you're trying to solve. And this can be as simple as, can we better predict the probability of cancer based off of image data? Or it could be, can we predict fraud at 1% better, right? You really want to have a question or hypothesis that you're really going towards when you first start doing machine learning. And the reason I like to start with that is because there's a trend, especially in the industry, where a lot of people just say, here's a bunch of data, tell me what the data means. But you need to have something in mind that you're trying to answer, something you're trying to solve, because I can tell you something from the data, but it doesn't mean it's of value for you if I'm looking at this data blind. So you definitely want to have a hypothesis when you're moving forward. After that, you want to really think about, so what is the data I need to address this problem? And once I have that data, it's where you start this data transformation. And data transformation is a generic term that means a wide range of optimizations to the data that I can do. For example, I might have character data or string data that needs to be converted to be coded. So I may have education level, and I may have no high school, some college, bachelor's or advanced degree. And for the computer to be able to understand that, I need to be able to do some data transformation to be able to code that into a numerical value for each one of those. And then there may be data where if I'm looking at income data, for example, because there's such a huge variance in data, I may do something like a log transformation to make that data look a little bit more normal. So when I say data transformation, it's really doing a lot of that data prep to get that data cleaned up and try to make that data as normal as possible for me to move forward with. The second part is this machine learning process that's on the right-hand side. And this is really that building the model itself. And what you do is you use a subset of data as what we call the training data. And then you'll have another subset of data that we call the test data. And then there's always the option to do something called the validating data set. So you can partition your data in 2 or 3s and move forward. But really the main goal here is this is where you're applying the mathematical process to the historical or behavior of that data to be able to start to learn the patterns from that data. And once you get a model that has the criteria that you're looking for, meaning it's as accurate as you need it to be, it's as precise as you need it to be, and there's a lot of steps going back and forth between that machine learning prep and this machine learning process to do more data transformation or include data, exclude data, to be able to get that model to where you need to be. And then once you have that asset, which just to clarify, a model is after you've learned from the data, there's going to be a mathematical formula that you're able to apply. So a model, and I'll discuss this a little bit later, can be logistics regression. It could be a decision tree. So it's taking that data and learning from it. And then I could go ahead and deploy that model to score. So we use the term score or inference, meaning I can insert new data against this model and determine a prediction based off of the new data. So maybe for fraud, if I use my credit card, I can determine new data and predict with a probability, is this a fraudulent transaction or not a fraudulent transaction? And this is what most people really think about what machine learning is. And this is where everyone, enjoys spending their time in machine learning. But to be honest, I would say the majority of your time will always be sitting in the machine learning prep stage. Probably about 80 to 90% of your time, and maybe about 10 to 20% of your time will actually be in this machine learning process. And then once you get through this part, this is where I talked about you needing a team to be successful. There's a concept called model management. And really what we're trying to do is just monitor our model's performance over time. So just make sure that we're maintaining a certain level of expectation with that model. So for example, I worked on a project where we were doing optimization of resources into a government agency. And then as people really started to optimize these resources, there's trends that started to change. And so your model is not as accurate as behavior starts to change. So you need to monitor how that is over time so you can go ahead and redo this process. So that's the reason I like to put this in this kind of format of a circle, because it's a continuous process. It's not you just build a model and you're done. You need to continue to learn from your model over time.
Can I ask a quick question?
Yes.
Can you go back to the previous slide, please? Yeah, you said we're going to spend 10% of the time on the machine learning process compared to the 75-80% on the prep. Why is the reason? Why is less time on the machine learning process?
Yeah. So in order for you to be successful in that machine learning process, there's a lot of just data cleansing and learning from the data that needs to take place. And that's really where the bulk of the work is. It's, figuring out what data transformations I need. How do I account for missing variables? How do I account for missing or null variables? How do I even account for outliers or data errors within the entry? So that's usually where a lot of your process takes place, in getting that data clean. So that way, when you get to the machine learning process, the computer knows how to create like an array with that data. So that vector that we mentioned before, to be able to really compute the algorithm that it needs or the model that it needs.
How about the 10%? Why it's easy to do the machine learning process nowadays compared to maybe 10 years ago?
Yeah, that's a good question. So nowadays there's a lot of models within statistics that you can use. So a lot of different algorithms within statistics, such as like logistics regression, decision tree, random forest, support vectors, and I'll talk a little bit more about those in the presentation. But really what it is there's a lot of frameworks now that really help utilize these packages a lot easier. So there's things, like scikit-learn in Python, there's Weka, there's SPSS Modeler. So there's just a lot of tools that help make that easier. So the main challenge is really getting the data clean to utilize those tools to be able to process the data.
Thank you.
And what I'll do is I'll kind of pause there, Dr. Zeinabi, and see if there's any questions that anyone has. I know that, trust me, this is a lot of information that gets dumped on you from my point of view. And so I just want to pause and give everyone time to kind of digest all of that. I know it's quite a bit sometimes. So if there's any questions, just put it in the chat and I'll pause maybe like 15, 20 seconds to see if there's any questions.
Yeah, I'm monitoring. Yeah, I see one question just came. So it's from Dr. Fox. So another one. Are you able to see the questions, Jamar?
Yeah, let me click on there. Yeah, I can see the question. So is it correct to say that one of the problems to using machine learning, it seems, is not in terms of the difference in conceptual approach to stats, econometrics, is the unfamiliar terminology, the performance analysis shown here is a binomial distribution, what economists call variables, or called instances, and so on. So Dr. Fox, I definitely agree, right? There is this, those vocabulary that changes depending on the field that you're in, right? Economists may use one term. I come from a very statistical background, so I may use another term. Someone from data science, may have it, but that's where at the beginning I was trying to say, let's get these buzzwords out of the way. It's really just, here's the process of being able to approach it with being able to apply some math to data, learn what that behavior of that data is, and then be able to make some predictions moving forward. That's really the main key. I'm definitely going to be trying to keeping the terminology more closer to data science and machine learning, but overall it's the same thing. Economists, statisticians, whatever it may be, we're all trying to do the same thing. We're just trying to learn from data.
Yeah, the next question is from Dr. Kapoor. How is this different from SEM, which stands for, I don't want to guess.
Yeah, I'm not sure what SEM is either.
That's standard, I don't know, education. Oh, standard education method. Dr. Kapoor, can you tell us what SEM stands for in the chat? Let's move to another question. How relevant machine learning is in a typical course? Dr. Falai Al-Sateh, how relevant is machine learning in a typical course?
Yeah, so I'm just going to kind of make the exception here, like a typical IT or, I'll just do a typical information science or IT course. I would say relevance is, machine learning is definitely very relevant, right? We're in a time where people are starting to learn from their data. They're trying to exploit their data more. And I know we kind of really latch in on the machine learning part, which is just the model development. But as I mentioned before, it's really a team sport. So if we look at it from a big picture, right, you're going to have data engineers and database administrators that really can help with that early data collection, data cleansing stage. You're going to have the data scientists that will be doing a lot of the data prep, data model building. You're starting to see a new role in the industry called machine learning engineer, and they're much more focused around the development operations or DevOps around machine learning. So in my opinion, it's very relevant. It's becoming more and more prevalent within different organizations, and it's becoming easier for more individuals to consume machine learning because of these tools are becoming easier to use. And so I think at this stage, it's one of those things that for introductory students, they should be just introduced at a high level to it. And then as they progress through, their program, having the option to have a specialization within data science or machine learning is definitely a value.
Yeah, I think
equation.
So. Yeah, SEM stands for structured equation modeling. So how is machine learning different from structured equation modeling?
So it is. So structured equation modeling, which it's been a while since I've taken a stats course. If I recall, the multivariate analysis method, right? So that is machine learning, right? It's machine learning is statistical processes within it. What I find is that a lot of people learn the top 10 algorithms, which might be like a logistics regression, a decision tree, a random forest, and those are the models everyone applies to everything. But to be honest, there's well over 50 different statistical algorithms you can apply to it. And so that's where I think this machine learning prep, where you ask the question or you have your hypothesis, will help facilitate that method that you use moving forward. So SEM is another method you could use for being able to do prediction against the model.
Yeah, I just want to add also the following, because we know statistical techniques, statistical methods, they are widely used. Generally, they require some kind of quantitative variables, especially regression, structure, equation modeling. All those require some quantitative. We have to change the variable into quantitative variable or numeric type data. But there are other additional new techniques which are called actually non-statistical techniques in machine learning.
Yes. Like
classification, clustering, association rule mining. There are a lot of similarity measures, all those things. So later on, we'll see with examples, it allows us also to deal with non-numeric type of attribute or variables. So of course, half of machine learning is done through using existing statistical technique, but there are other, I would say more than 50% new techniques, new algorithms already developed. And also in a new kind of data we're dealing with, like image, like videos, like text, The natural, that's the parts. Also, I think what's one important thing is, I know Dr. Alsate and his colleague did a research on artificial intelligence in business. The main driver in artificial intelligence is machine learning.
Yeah.
So most artificial intelligence is enabled through machine learning. So it's everywhere, in every discipline. In 5 years, I would say business students, they need to understand that and be able to work with system who have some intelligence embedded in it.
Yeah.
Yeah.
And that's a good point. I would probably make the case that all AI that you see today is machine learning, and then a subset of that is deep learning or neural nets, which is just a just a hyper specialization of machine learning. And then the cognitive computer that everyone thinks of that is machine learning probably won't be around for a while. That's not until we get to the ability of more advanced technologies like quantum computing and things like that. So, when I say machine learning, I think a lot of people try to take it into like it's computer science, it's stats. And really what it is just the merging of these two fields. Sometimes, with business or sometimes with like psychology, but it's just really merging of computer science, statistics, and learning from data. So the next few series of slides, what I want to do is just really break this down into a concept. So again, I've been talking, 30,000 foot view of what machine learning is. So let's just kind of walk through some very, very simple experiences of what machine learning is and see how do you utilize this. So the first one is around house prediction. And I have the square foot of a house on the left-hand side, and we just have a few data points for this. And then that's what we call a feature. So a feature is really just an attribute, a column, where there's going to be information for the problem we're trying to solve. So for predicting house prices, you can definitely extend this out to be, number of rooms, number of bathrooms, lot size. So there's a lot of different variables you can start to put into this to make it more complex, to have a better prediction. And then what we have here is called the label. And the reason we call this the label is because that's what we're trying to predict. So that's the price of the house. So we have a feature, which is the square foot of the house, and then the label, the price of the house is what we're trying to predict. So this is what would be the training data set here. And so this is actually a regression problem. So, and what I mean by that, this is a simple linear regression. And it's one of those, it's an XY plot where I can say within this is here's the square foot. I can make an approximation to what that price might be. So if we look at this here, I have some plots of square footage and price of a house here. And as you can see on the y-axis, it's just price in hundreds of thousands. And then we have on the bottom the square foot and thousands of square feet. And you can tell it's not a perfect line through these data points. Really what we're doing with machine learning is we're making the approximation of what's the shortest distance between all of these points to the center of this line here. And that could be from what we say in generic statistics terms like the mean or the median, but it's really just looking at what's that difference between all of these here and what we can do. And for example, once I have an algorithm that can really tell me or be able to plot this prediction, is if I had a house that's 2,450 square feet, what would be the approximate price that I would be able to sell this house for? And we can see just based off of this model here, it's 210,000. So if you really look at this top right-hand side, right, we have the price is a sum function of the square footage, and that's my model. And then there's going to be some weight tied to this square foot to be able to say, okay, something times this square foot will give me the price. And so we're just really assuming that this is a pretty accurate model. So if we go to the next slide, we have something called fit. So in that last picture that I showed, we have this middle line here where we have B. which is that weight that we're looking at. So for this example, for B, it's 0.8 times the square foot gives us a pretty accurate representation of what the house price could go for against the square footage of the house. But in machine learning, there are different weights that may come up based off of the data. So if I had some outliers that came further out to the left, I might get something that looks like C, where it's 0.5 square foot. And if I had more outliers that, to the right, and then if I had more to the left, I would have the, 1.3 times the square foot, and it gives me a different price set, right? And then there's also this concept here of error. So the error is, if I were to make a prediction based off of, let's say, 4,000 square feet, and I'm looking at something that might be around 350,000 in price, but in reality, it's around 300,000. That difference between what I get is an error rate, and I can calculate that for all of them to give me the overall error rate of my model. And that's where we start to look at things like accuracy and precision on how well I can predict. So accuracy is how accurately do I predict the house prices, and then precision is how many times do I do that accurately. So if you kind of think about it, if I was throwing darts at a board, and I get everything in the bullseye, that's accurate, and then I'm trying to aim for the bullseye, that's precise, right? But let's say I get everything collected around the number 2. It's accurate, but it's not precise, because my goal was to try to be able to hit the bullseye. So that's really the main difference, is how well things are grouped together versus where we're trying to predict it at. And I see a question, a comment, I guess, of the labels, the features, not dependent and independent variables. So again, this is where that terminology in the data science field. So features is independent variables, and then you have the dependent, which is sometimes the label. But that's not always the case. You may have dependent variables within it. So in machine learning and statistics, right, we sometimes make an assumption around what independence is and what the dependent variable is, but overall it's the same concept. Is we're trying to take these attributes or features and then predict something that's dependent on these features.
I see also one question, I missed it earlier, I apologize. Would it be correct to say machine learning is in its early stage of development?
Yeah, I would say so. Like, I would say, again, machine learning and the statistics field has been around since the late 50s. And now that we're at a point where the technology can actually perform at scale of what we need, that we're in the very early stages of really getting this off the ground to be utilized in more effective ways to do better predictions and to do automation of a lot of tasks, right? In this presentation, I don't go around like the ethics and things like that, but there's obviously a whole nother part of that where we have to really consider the ethics and impact. But overall, it's still in the early stages of how is this going to transform industries? How is it going to transform society? Things like that.
Yeah, I'm going to say generally AI, I think it's well developed in terms of its development. It's well developed, including machine learning. I would say its application is in the middle. I think most business in the background, they use these techniques to make a lot of decisions, including loan application, some of the application Jamar explained at the beginning, in a school admission. So it's widely being deployed and used. And it's everywhere now. So
yeah,
it's
exactly.
well developed. It's well developed and it's widely used technology. And even in some literature, they expect business graduates and also other graduates to understand this and be ready to work with this new technology. To work with, I'm not saying to create, because they're already in the organization. It's like Word, Microsoft, or any app. So future students or future graduates, they should be able to understand and use these apps and products.
Yes, I agree. And then where I'll say that machine learning is really much more mature is around repeatable processes, right? Like if your organization has a repeatable process that is something that a computer can really learn from, that's sort of like the low-hanging fruit in machine learning. Even in the corporate world, right? A lot of customers start with those processes that are repeatable, and I can teach a computer to learn those processes and then automate that step. Really using machine learning is what I'm doing there. So this is the slide. This is just a visualization of from the last slide when I talked about error. And so you can see how far off I am from this line, this prediction line here versus the actual. And that's one thing I do want to highlight is when you use machine learning, you're making a prediction, right? So it may not always be very accurate, but based off of the math, right, I can make some assumptions and I can do some adjusting with the different error and, even change this algorithm to be able to be more precise. There's things that we have to worry about there around like overfitting and underfitting, but overall I can be within a very close ballpark of a prediction that allows me to be able to make next steps. So Dr. Zenabi said, loan applications. There's things there that I can go ahead and make some early predictions to be able to process loan applications. A big one that I actually worked a lot with is with insurance companies. And there's when you submit a claim to an insurance company, let's say for a car accident, there's a whole process on the back end where they can automatically process that claim so they don't have to have a lot of touch points there. And so you want to make a prediction is, will this claim make it through my automated process system, or will it fall out and require a person to be intervened? And so that's I can do pretty well prediction with some error there to be able to get a person involved. And then what I like to do with that transition from when we talk about the error is there's times where we're more accepting of a higher error rate than others. So for fraud, for example, we really want to try to be as accurate as possible because of just the impact that fraud can have to a business or to an agency. And so that, we want to try to be as accurate as possible. But something like in healthcare, so when I worked in breast cancer research, there were times where we would take a higher error rate because we would rather have someone go get a second opinion versus we predict, a false positive or a false negative where we say it's not cancer, but it is cancer's tumor. And that person is living life as if they don't have cancer, right? So there's times where you're okay with that error rate not being as high as possible or, being higher than as low as possible. So that way you can go ahead and have a follow-up if need be, if you're on the borderline on where you're at. So I have another data set that we're looking at. So the previous one was a linear regression where we were, doing a line against a continuous variable. So meaning we were looking at square foot against price, and the price of a house can be any variable above zero potentially, right? So this here, we're doing something called classification, where we have a simple classification, is this cancer or is this not cancer? And we have some data here. And so we have two features here and we have one label here. So the feature sets we have here is we have age and then we have tumor size in centimeters. And again, it's the same process as we're trying to see between these two features or variables, can I predict if this individual will have cancer or not based off of this information? So in the classification model, what we're really looking at is we're trying to group these two things that we're trying to predict in this case, and this is what we call a binary, right? It's either yes or no. You can have a multivariate. So how do I classify maybe customer segments? So there's multiple ways to do this, but really what I'm trying to do is classify this a yes or a no. And then I have what's called the best fit. And I can have two options here, right? I can have this C line that goes all the way through evenly between, and ideally I would be able to have a mathematical formula that would be able to put yes or no between the two lines, or I can do A, right? Because I have an outlier here, but overall it's fairly accurate. So this is what is the best fit for a classification model. And this is the challenging part. This is where that iterative process takes place within machine learning. Is there's a million ways to do this, and the goal is you do an iteration enough times where it converges to a point where this line isn't moving as much to be able to help make a better classification model. But it can definitely be challenging in this kind of arena, but this is really what the computer is good at. This is what those algorithms and statistics are good at doing. So in this case, what we're doing is we're doing something called a logistics regression. And this is where, even though it's called a regression, it's still a binary system. It's still a classification part. There's other things called like a decision tree or random forest. These are very common as well. But what it is the computer has a probability of having a disease, and what it's trying to do is move that line to be able to put points at a highly accurate method away from that line. And the further away that a point is from this line, the better that prediction would be of, yes cancer or no cancer. And so there's, at the bottom here, there's dozens of classification algorithms you can choose from. A logistics regression is a simple one to use, and it can be very accurate over time.
Yeah, there is one question from Dr. Badabanga. Looking at the fitted line, it's obvious that it doesn't have to start at the origins of axis. Can you use a line that starts somewhere above the origins? That means an intercept is required, or the square errors will not be minimized.
Yeah. So in this case here, right, we're trying to put a visualization onto this algorithm. And yes, it does not have to start at the origin, right? You can have a weight, and then I can have this be, what if it was, everything below 2 centimeters was no, and everything above 2 centimeters are yes. So my line would actually be like this vertical line that splits the data, right? So for this part here, I'm not really concerned about where the origin of this is. And I'm more focused on what is the distance between this data point here and the line versus this data point here and the line, and being able to accurately classify those two. Same with the regression that I showed earlier, right? We made the assumption of the origin starting at 0, but there could be a model, right, where you have a constant as part of that. So I can start at maybe, the $1,000 mark, then from there have my function of square foot times price plus that 1,000, right? And gives me pretty accurate. So it's much more of what assumptions are we making? And then also, what am I trying to accomplish of where that line or that split may be for something like a regression or a classification model.
Yeah, I think he's referring to the previous regression or example, not to this. Yeah,
so the previous one, again, I can have a constant that helps better predict. So It doesn't always have to start at the origin.
Good. Thank you.
All right. So another one here that I could use for the same use case is called support vector machines. And what I'm trying to do here is you're trying to find a line that misclassifies the fewest points possible. So really what it is it separates the points with the maximum margin between the two. Logistics regression is doing, pretty much the same thing on a simple basis. But what support vector machines does is it has the built-in iteration within this, right? So I can say, I'm going to start with a random line. So that's your assumption of this data. And then I can iterate until I get to a point where I have the lowest error rate between misclassification. And this is where machine learning this is where the computation shines for machine learning, right? Because we could do this by hand statistically, but this would take a very long time. We couldn't really do that many data points. But now as the computation has gotten here, I can iterate like 1,000 times very rapidly over this data set to really get this line to start to like merge to a point where I can, do the best classification between the two. So before I kind of talk a little bit about some of the common machine learning algorithms, I just want to pause again and see if there's any questions from the students on, machine learning, the process of machine learning, on just this high level conversation that we're having here. So some of the students in the chat, just put in, is this making sense for you? Is this helpful for you? So that way, as we go through this presentation, just let me know if there's anything I need to change to really make sure that this is of value to you.
Yeah, so I think, while waiting for students, I'm going to give a couple of comments. First, my background is similar to Jamar. So I did statistics. Luckily, I started being willing to learn a new approach to data analysis in 2005, and it took me a while to make the mindset shift. So I know some of the examples we just provide are still, they are dragged to statistics. Later on, Jamar, and also I will show you some, completely different problems, similar problems, but completely different approach to building model. So I know logistic is widely used, but there is a lot of limitation to it. You have to have a numeric independent variable. You can only have 2 labels or 2 class values, right, for the dependent variable, yes or no. Yeah. But most problems, they require, they have many, more than 2 possible values. For example, let's say level of the cancer stage. There are stage 1, stage 2, stage 3. Let's say stage 4. So if you want to build a model that will classify a patient to different stage, I don't think we'll be able to use logistic regression easily, because there is more than 2 possible outcomes. It could be stage 1, stage 2, stage 3, or stage 4. So also on the independent variable side, we need to make all quantitative, right, even to fit the regression. Yes, we can always create dummy variables for every possible values, but that's tedious. Yeah. Through the new machine learning techniques, you can use the attributes, the variable as they are. For example, let's say ethnicity of a patient, or whether it's African American or Hispanic, or what's the other, white. So there are many possible values. So for that, we don't need to create a dummy variable for each. We can use those techniques. So even we deliberately make this example simple, but still, our statistics are pulling us back to those old techniques. So as we proceed, I know Jamar is gonna show you more examples. Let's see. Yeah. Okay, and I don't see any question, any comment you want to make, Jamar, before we proceed?
Yeah, so I do see one question where, someone asked about the approximation of the problem using different functional forms. Yes, so there are different classification and regression models that are going to be, they can be exponential, they can be quadratic. So there are different variations even within the classification, or that's where you start to get to like more of the multivariate analysis. I start to get to the exponential potentially. It's really going to depend on my data and how I tackle this problem. And then I see another question here. It says, would you say that machine learning gives better or more accurate predictions? Does machine learning help to address this notion of causal inference? So not always, right? Machine learning doesn't always give the best or more accurate. It's, that term garbage in, garbage out. It's really going to be dependent on how good your data is, how well you have your hypothesis or your question structured, and then the method and techniques that you use. And that can take sometimes, like up to a year or a year and a half to really get those, get to that level of accuracy or the better prediction than you need. There are times where, there's been a lot of times where physicians have continued to be better than the machine learning algorithm to be able to do prediction based off of just experience and more input that they get from the patient versus just, some numbers or data in a database. So there are times where machine learning can help augment those decisions to be a little bit better. And then, so there's this concept within statistics and machine learning, right, that correlation is not causation, right? So this inference about what causes. There's still a huge challenge of being able to say this causes that. But what we could do is we can say there's high correlations between things. And then that's when you can kind of get to the qualitative part of it, where you can say, okay, this is definitely something like a root cause analysis. Like this is a reason why this does take place, right? And that could be within a system, that could be within the process. So there's different ways to be able to look at that, but it's still very challenging of just the causation part of it. You still want to represent that accurately around errors, accuracy, as well as, is this truly the cause of what's happening here? So with that, what I'll do is I'll kind of talk about some common machine learning algorithms and methods. And the first concept is around supervised learning. And I have another slide where we talk a little bit about this again. And supervised learning is, I've been keeping track of my data and I knew the historical outcome. So for example, with fraud, right? I may keep track of fraud. I may keep track of loan decisions, right? And then I can be able to use that to train these supervised learning models. So that means based off of the fact that I've kept this data, I can go ahead and utilize this to learn from the historical trend and predict out that value based off of what's happened previously and with my data. And some of the common models here is something called a decision tree, a random forest. So those are really, I have a picture of what they look like, but it's really what you think. It's like a decision tree of all these branches coming together and making a decision. Then you have logistics regression or linear regression, and that's what we really focused on in some of those use cases. And then you have something called the K-nearest neighbor and naive Bayes. And those are two things that can be blurred between supervised and unsupervised, depending on how you apply it and what data you use. But a lot of times people try to use this within a supervised method. And the way that those are used and trying to make a prediction of something. A really cool way that I've found out that naive Bayes, for example, is used is that there was a plane that went down in near Spain in the water, and they really used naive Bayes to be able to make probabilities of where they might be able to find the plane and be able to narrow down the search. And because of that, they were able to get to people and save lives a little bit sooner because they use that method. So there's a lot of different ways in how you can use this, but it's more of you're making some predictions and insights into something. The next step is what we call unsupervised learning. And this is where we don't have any knowledge of the outcome before or during this. So we're letting the computer really tell us, these models really tell us what's gonna take place on how do we do something. So some common ways of doing this is k-means clustering or hierarchical clustering. And really what we're doing here, an example that you might see with this, and you probably experienced it quite a bit, is clustering customers into different segments, and then they do upsell or cross sell to you. So you've probably been on Amazon and seen that, based off of other customers' behavior, here's some recommendations of some items you may want to purchase with this, right? And really what they're doing is they're clustering you into a segment of customers that have a similar purchasing behavior. And then based off of that, they can start to figure out, okay, how can I better make some advertisement to you to have you purchase more on the platform. There's anomaly detection and outlier detection. So this is much more focused around, just looking at something that just doesn't belong within the system as we expect. Anomaly detection is used quite a bit in cybersecurity, for example, to determine if there's an anomaly within the network. So is there someone in the network behaving unexpectedly? And, we can make some assumptions that maybe this could be malicious and that we need to take action. But that's really how a lot of like this takes place, is really looking at the anomaly detection. And then another form of that is neural nets and deep learning. And that's where a lot of people are starting to do a deep dive here. Google is very well known for this with TensorFlow. AWS is known for this. This is where you start to really take advantage of all of the computing resources, as well as the math that's been developed with deep learning to make some pretty good predictions on images, video, natural language, things like that. So that's where a lot of things are starting to go. And then you have this this reinforcement learning. I kind of like to group into a third part of machine learning. And where you see this a lot is actually in robotics and self-driving cars, right? So reinforcement learning is for a car, for example. If I'm trying to get a car to be able to drive, let's say through the campus at Bowie State, right? I want to make sure that it's going to stop at any stop sign, that it's going to stop for people crossing, it's going to stop for cars that may be there. And so what you do is you would use this model to teach the car. So if it didn't stop at a stop sign, you mathematically say, okay, you didn't accomplish the task properly. So, this is not a reward. But if they stop at the stop sign, you mathematically give that algorithm a reward. And so anytime it does something you expect it to do, it gets more of a weight on that and say, okay, every time I stop at a stop sign, I'm more weighted to do that. And so it's really just learning as it goes. Same with robots, right? If I'm in manufacturing, you want to use this reinforcement learning to make sure that it's properly doing the function that we expect it to do. And I'm going to be pretty brief on these because the goal today isn't really around deployment, but I did want to just highlight it because it is something to really think about. And so I'm not sure who said this. I heard it before, but they said that the great divide in data science is this model development to deployment. And it's very difficult. We have a lot of smart individuals and a lot of research and development that has gone into building these models and being able to predict a lot of amazing things, but to put it into an application that I can actually use has been very challenging for people for many different reasons. So I just want you to keep that in mind as we start to talk about machine learning. There is the need of how do I actually utilize this in a way that can benefit the organization, that can benefit research, that can benefit society in general. So there's a lot of thought to go into this, but I just want to highlight that this is a challenge that a lot of people are trying to work with now. And so really when we think about deployment, we're really looking at, so do I do real time? Do I do batch? How do I scale this? How do I enrich my features? So add better data. And then this model management piece that I told you before is how do I make sure that my model is still performing over time as I expected? And then this is a big one here, this explainability. And this is where machine learning in general, and data science in general, has to consider ethics and impact on people as well. So I have to be able to explain why my model made a decision that it made. So if I'm denying someone from a loan, I should be able to explain that because there's historical behavior of banks that have traditionally left people out of getting loans. So if you use the same data that you've had before, you're going to continue that same harmful behavior moving forward, right? So you have to be able to, one, understand that there's bias within this data and make a change to that data, and then two, be able to explain why your model made a decision as it goes forward. So this is a key point as things move forward, and this is becoming more and more of an issue, especially with things like neural nets and deep learning. It's actually very hard to explain why those algorithms made the decision they made. There's starting to become tools out there to start to do that, but it is critical as we move forward. So I just wanted to say that, like, there is ethics that have to be part of this. Even though we won't dive deep into it, it is something I still want everyone to kind of think about in the back of their head as they start to learn more about machine learning and data science. All right. So this will be the last slide for the part one, not for the whole thing, but just for that first intro to machine learning. The next sets of slides I have are going to be actually doing the model development. But what I want to do is I want to really just talk about why machine learning. And so it's really to tap into the rich value of historical data, right? There is still a lot of value in this data that we have floating around to be able to make decisions. And really what we're trying to do is we're trying to discover new insights within this data and, be able to make better decisions. And the one thing I'll say is that with my experience, many organizations and institutes, whether it be education, the university, or whether it be Fortune 500 companies, they're really good at generating these reports to be able to tell you what has happened. But a lot of customers are that I've worked with, and a lot of agencies I've worked with, they're really trying to say, okay, how do I get to a point where I can do some predictions to be able to better utilize this data that I have? And then there's a wide range of use cases that you can use for this. Fraud detection, loan approval, optimization of resources. So how do I deploy, my employees a little bit better? There's just a lot of different use cases. And I would say overall, in just the arena I've been in, the two main things that a lot of people are trying to use machine learning for is, how do I either generate new revenue, so new lines of business, or how do I do some savings? So how can I optimize my organization to perform better? So it's just really that. And then the last thing here that I wanted to talk about before we go to the second half of this presentation is the development of machine learning is a team sport. So there's the part to be able to examine and develop those internal resources that you may already have. So data analysts, data engineers, business analysts, developers. And really what the goal is how do I help infuse my business or my organization, my institution with machine learning to be able to help make better decisions? Like I said, I've been much more in the business space, so I kind of geared a lot of this towards business in general. But really what I'm trying to do is, like, how do I collaborate better? How do I use these tools to be able to make sure that people that are subject matter experts, so maybe someone that deals with loans day to day, but may not be on the tech side, how do I work with them to be able to merge that gap between the business experience they have and then the technology experience you have with building machine learning? And then one of the other things I always get questioned a lot is, well, is machine learning going to take over everything, right? And like I said before, if there's stuff that's very repeatable and redundant, there's a good chance that automation can come there. But there's still always going to be a need for humans as we move forward. There's going to be new innovations. People need to still continue to solve new problems and gain that experience as they move forward. So the main reason of something like today of learning about what machine learning is being able to understand is, how do I put myself into a position to be part of the changes and development that's coming along with machine learning and be a participant in this versus just an observer moving and just seeing what's happening here. So what I'll do is I'll pause there. The first half of this presentation on what machine learning is complete. Let me know if there's any questions that you may have. And then I don't know if we want to take a break before I start part two, but we'll kind of go there. I do see a question here that I do want to talk about. So in your opinion, do you see algorithms evolving to account for ethical issues around systematic racism? as of right now, what I see in the field, it's not doing a good job, right? This is where we need like better practitioners to be able to be in the field that understand what the societal impacts can be of machine learning. I do see people that are starting to look at it and say, okay, we have to make a decision of the ethics of machine learning and how that is. So in my opinion, I think there are people that are trying to make sure that ethics becomes part of overall what machine learning and AI becomes. And for example, and again, this is just in my opinion, right? Like, I don't think there should be any machine learning in the criminal justice system just because of how historically impactful it's been negatively to Black individuals, right? So if you were to keep learning from that data as you do, you're going to continue that system that is in place now that just it's been more detrimental than it has been helpful for any of our communities, right? So there has to be this discussion around ethics. And that's where, when I talk about a team sport, that's where not just in a business case, but in an interdisciplinary case where things like philosophy and psychology and stuff like that starts to come into play of how do I create ethical systems within machine learning to do something that, like in when I worked at the Cancer Center, when we did machine learning development, it was always with the pretenses, what harm will this cause if we deploy this, right? If we make this into production at the hospital, what potential harm can there be? And you have to really just think about it at a very high level and think about it as many different use cases there that you can think of where that system might not act as the way you thought it would.
Yeah, I think that's a great answer. In addition to that, I think this solution that includes AI, machine learning, whatever outcomes they produce, they need to have a mechanism, a capability to explain how they arrive to that outcomes. So there is accountability pieces included in the system. So there is a large movement because these systems are making decisions such as, for example, home loan approval. So to make sure they are not discriminating based on race or other characteristics. So they need to be able, the system, the software, the algorithm, the computer need to be able to explain how they come to that conclusion. So that was not initially there. Now they are required to provide that. So the ethics, the accountability pieces is getting, I think that's the trend in research in that area. There is another question by Dr. Alsati. I think Jamal, you might need to take a break, maybe get a cup of water.
So I'll answer the two questions here. We'll take maybe like a 5-minute break, and then I'll start the second half of the presentation. But so just to briefly elaborate over deep learning is, and I'll talk a little bit about it in this next coming presentation, but what I'll do is I'll save probably about 30 minutes for our next part 2 to really talk about deep learning, because it is such a big field right now and it's booming. But what it is it's a subset of what we call neural network, and neural network is the attempt to try to mimic the human brain in the way that information is passed through different nodes and different layers. And then deep learning is a specialization of that, where you create these mini layers of mini nodes to be able to pass a lot of data and learn from it, to be able to give you things like being able to show a stop sign on an image, like be able to predict that this is a stop sign or this is a bus. So that's really what deep learning is. It's just a specialization of what we call neural networks. And then for data integrity, I would say it's a huge deal, right? And that's that garbage in, garbage out. And it's both with an ethical point of view, but as well as just a practitioner point of view of making sure that the data that I have, I can trust it. So is it entered correctly? Is there any outliers or data, data error entries, things like that, where I need to be aware of the data. So One example I'll get there is when I worked at the hospital. Sometimes someone might enter in the treatment that a patient got with chemotherapy, and they might enter the wrong number when they're doing the data entry, even though the patient didn't receive that much. So there is a key of like, how do I make the data integrity a key part of my machine learning process, and that's that data engineer, database administrator job to be able to do that.
Jamar, take a 5 minutes break. Any other question? Again, I know Dr. Sengupta asked for a good example. Can we select something more cheerful as an example? I agree. We need to have an example which is far away from traditional statistics. I have an example. Will I be able to share my screen, Dr. Brown?
Yes, let me see. Let me end the slideshow and then we can pick back up afterwards. So, well, actually, I don't know, Dr. Zimby, try clicking on turn your screen share on now and see if we.
Let me see if I can share. What do I have? Oof.
It's right beside the microphone.
Yeah. It's, I'm trying to make sure I have the.
You're fading in and out a little. You did that.
Okay.
Dr. Sengupta said, not breast cancer, please. We already have COVID.
I like that one. I like that one.
Do you want me to stop the slideshow so you can share it? I can stop the slideshow.
Yeah, let me share maybe the use case example one.
Okay, so I'll stop right here. All right, go ahead. You can you should be able to share your screen now.
Okay. I'm trying to enter Chrome. Is it in the Chrome? All right. Let me share this.
You're kind of scratchy.
How about now?
Okay, you're good now.
All right, let's say this up. Data sets. Typical data set actually
okay, that's better now. I'll let you know if you fade in and out again, but I think you're good now. Okay.
So you can see this is an example of the data from customer who subscribe to.
Oh, your mic again. I'm sorry. It's your mic again. Your mic is fading in and out again. Dr. Zinabi. Your mic is fading in and out again. Yes, I can hear you now. Whatever you're doing, stay in that same spot. Okay.
All right. Ooh. So again, this is a typical example where the goal is to determine which of these customers stay or leave.
Oh no!
So when
we can't. Okay, go ahead. So can you repeat it again?
So this is a classification problem.
You're still fading in and out. I'm sorry.
Company or leave, so they call it custom.
We can't really hear you.
Let me
can you take your mic off? Yeah, check your signal too. Your signal, it's in the right hand corner or where it says signal, and you might want to take your you can take your mic off as well and just talk to the computer. That might be better. I can't hear you now. Jamar, you're still there, right? He must have stepped away. Okay. Well, I guess
Can
it's
you hear
just me
me?
here talking. Yes, yes, we can hear you now.
Yeah, so the example is this is a customer retention.
All I heard was customer retention. All I heard was customer retention.
Yeah, you
If you want to take a screenshot of the file and then sorry
better
y'all, I got
now.
noise on my end. And then send it to Samantha. We can upload it in the files. It might be better because I think your frequency is messing up from the screen sharing and the talk and the microphone.
No.
So if you want to, you can send the file to Samantha, and then she can upload it.
It's okay. It's okay. Can you hear me now?
Yeah, we can hear you good now.
All right. So let's see.
I'm gonna hit mute again because I
Where
got a
are
lot of
we?
noise back here. Would you like for me to set up the slides again? Here, I'll set up the slides.
Let's see.
Do I need to go back? Okay, thank you. You can take over, Jamar. So, Jamar, I believe Dr. Zenabi probably had to log out and then log back in. So, let's give him a couple of minutes. Can you say something, Jamar? I just want to make sure I hear you. No, I can't hear you. Is your mic on? It should be blue at the top. Okay. Yeah, I can't hear you. Let's see. You might have to log back. I don't want to lose you. Maybe it's mine. Let me see. Can somebody in the chat let us know if you can hear us? Jamar, I think I hear something now. Say something, Jamar.
Yeah, can you hear me now?
Yes, I can hear you now.
Okay.
Okay, great.
Perfect.
All right. So I'll go back and be quiet again. All right.
Not a problem. So let me put my headphones back in so that way hopefully I'm a little bit more clear. So the second half of the presentation, what I want to do is I really want to focus around machine learning and the model creation or algorithm creation, and do a deep dive of what that looks like, what the process and the steps are, and the things that you need to think about when building a model. Before I start, I do want to highlight, like, I know, one of the jokes is the use case and being a little bit happy. So one of the things is I love like the hard problems. So with working at the Cancer Center, one of the things I learned is if you do this right, you can have positive impact. So a couple of the policies that I helped implement at the hospital, I actually helped change the treatment that people received, and then the populations that were reached out to make sure that in particularly Black women and Native American women got the resources that they needed. So I know sometimes these use cases could seem a little bit dire, but it definitely can have a great impact if done right. So the goal of this second half of the presentation is really to provide more information about just that machine learning model creation and some of the tools that are used to do that.
Jamar, let me check if everybody's hearing you.
I can hear. Can somebody else in the audience let us know if you can hear us?
Yeah, I see some Gupta and Dr. Alsate says initially I can't hear you. Yeah, go ahead. They can't hear you.
Okay, perfect. All right. So I briefly touched on this in the last presentation, but let's talk about the types of machine learning, right? And this is what we'll take throughout this presentation as we move forward. Is there's the supervised learning, where I had mentioned before that models are trained on label data. So when we looked at the predicting of the house price based off of square foot, we had the label data that said, here's the price of the house previously. And so we were able to use that to train the model to be more accurate of prediction. And so that's whether I'm using classification or regression model here, I can make that supervised prediction based off of the label data. With unsupervised learning, again, like I said, you have unlabeled data, so I don't know the outcome. So what I'm trying to do is cluster my data into ways that I can segment my data and do it fairly accurately. So one example of unsupervised learning, I worked on a project before where we were trying to determine where should the telecom network company put their towers for mobile reception, right? And so they really don't know where the towers may go, but there's certain factors that they're going to consider, such as tall buildings, the tree line that may interrupt the signal, the population that they're trying to target, meaning like, can they get the most amount of people touching this network within the city, things like that. So there's a lot of factors. So you take all of these labels and you're able to help create a few locations where you can put towers to reach the most amount of people with the least amount of disruption to their experience. So this slide is, there's definitely a lot on this slide. So what I want to do is just kind of break down this workflow. And the reason is data can be very complex as we move through this process, and then trying to build that machine learning model, right? So that first part that we have is really looking at the data on the left-hand side. And so we're looking at, the traditional business data. We're looking at new things like Internet of Things and sensor data. We're looking at, collaboration partners. So if any of you have experience of maybe taking social media data to utilize, you may have data like, for example, for the MLS for housing data. And then we're generating a lot of data on our phones every day, and that's the geotagging data. That's your data that you're putting in pictures, the hashtags you're using, all of that stuff. And then there's what we classify as legacy data. So that data that's been on some of this older technology that we still need to incorporate to be able to really do a good job. So it's a huge amount of different data sources. The data can be structured in many different ways, and the goal is really moving that into a phase where we could do the data preparation. And this is where we have a lot of computational resources used to do things, to create the training data set, to create this data set, this testing data set. And I kind of have it as broken down in time, but this data preparation can range from hours to like a week of work. So it can take a lot to be able to get all of this data and pre-process it. And then you have this third box, which is the model training. And this is where, we're really trying to build that model. And there's a lot of different tools here that we can use. There's going to be a lot of optimization that we're going to attempt to do to the data, to attempt to do to the mathematical model. And we're going to iterate over many different steps here. And this part can take weeks or even months to really complete this process of training the model. And then we have the production side, as I mentioned. So now that we have this asset that we built to do the prediction, we need to be able to put it into an application or a tool to use to be able to have benefit from this model. So this can be a very complex workflow, but no matter whether you're doing this on your own computer or you're doing this for a corporation? Are you doing this for the university? It's going to be pretty much the same. You're going to get some data. You're going to have to do data preparation. You're going to have to do the model training, and then utilize that model to do some kind of prediction or be able to help show what that model can do overall. So let's start with that first phase of data collection. And what I'm going to do is I'm going to take this from much more of a practitioner standpoint of just the experiences I've had with working with different agencies, different customers, and just kind of put it into that context. But again, like I said, this applies to you no matter what arena that you're doing machine learning model in. So with the data collection, there's this trend of creating what's called a data lake. And one of the most famous data lakes that most people have heard of is Hadoop, right? And what we're doing is we're creating these database systems that allows me to be able to move all of my data in there, whether it's structured data or unstructured data in the case of Hadoop, and be able to have a centralized location. And there's other tools out there, like there's Oracle databases, there's IBM databases, there's the Google Data Cloud instances, there's AWS in a lot of their cloud databases. So it's just really, where do I want to store the data and what type of data am I trying to store? Is it all structured? Is there some unstructured data? Do I have images, that have videos, things like that? And I'm trying to put this in a clean format. And this is what the expectation is you have this nice clean lake that you can utilize and pull data from when you need to, and be able to maximize the value of the data within the organization. In reality, the data lake is a challenge for many people when they're trying to do the data collection. And the reason is that, data is not always clear cut, right? It may come from a transactional system I may have. I may be pulling social media data. I might be pulling some IoT data. So I have this data coming from all these different points of generation. And then, I sometimes do some pre-processing, sometimes I don't. And what I'm doing is I'm just cramming all this data into a place. And unless I've really set up a lot of systems to organize this data, it's just becoming a dumping ground for all of the data. Then we're trying to figure out, like, okay, how do I get access to this data? How do I clean this data? Who has the right to access the data? All of these things that we have to consider even before we get to the machine learning part. And so the key thing here is really thinking about stuff like data governance, data integrity, data management. So that way I know that the data that I get is the most accurate data. I kind of have a source of who may have touched that data. And then I have the ability to know that it's the most current form of that data, right? So there's a lot of things in consideration to think about when you're getting data. So now that we've gotten this data collection going, the next step is what we call data curation. And really what this is how do I handle the data overall? So we'll have a data schema most likely. So that's just the layout of what the data is, right? So do I have character data? So how long is that character data? Do I have, data that might have a decimal? How many decimal points does it have? So it's really just looking at that. What does that data look like on the data schema? We might have to aggregate multiple data sets together. So I may be joining, customer transactional data with social media data. And, how do I join that together to get a good picture of what's happening? And then this is where you start to deal with missing data. So how do I handle missing data? Do I just go ahead and remove the data from my data set to move forward? What implications can I have? Is there something maybe that I should put as a placeholder in that value? So there's a lot of things that you got to think about with missing data. The next one is really thinking about noise reduction. So noise in data is that, it can be bad data, it can be outliers within data, but there's just, as you guys know, data is not always perfect. So when we talk about noise in data, it's really, so how do I handle data that may have an entry error, that might have a large group of random outliers for some reason? or just is bad data in general. So is this data that I can even trust? And then from there, the next two is really just like around how do I scale my data? How do I clean my how do I think about my data in terms of removing any identifiers, anything like that, right? And then the last one is that recoding or dummy coding is what we call, and that might be changing the column of male female to a numerical value to represent that, right? So we're coding or creating a dummy variable from that to be able to have a better data set. So what I want to do is I kind of just want to pause there. And so, we briefly talked about that workflow. We talked about the data collection and, now some of this data curation, which is part of that data cleansing phase. So I just want to pause and see if there's any questions or even comments that you guys may have about that. So next we'll talk about data exploration. And so for this slide, I've been spending a lot of time with my niece lately. And so she loves Moana and Dora the Explorer. And so I had her help me create this slide, and she really liked this. So I thought it was a good representation of the exploration, right? So let's talk about data exploration in terms of what we need for machine learning. And so the first thing that we have to do is we do some measurements of this data. And the key thing here is we're trying to look at the shape of the data. This is the biggest thing here of these, right, does my data have like the traditional bell curve, right? Or is there an outlier that is on the tail side? Or is there an outlier, do I have a tail that starts low and then goes high towards the end? And so you're just really looking at what does my data look like overall? And that could tell me a lot about my data. And then these next few things, these next 3 items or 4 items really is really around the traditional statistical methods, right? So what's some of the mean of my data, the median, what's my standard deviation within my data? So my variance, so how far does my data change from the mean, or it could be the median as well. So how does it deviate? Skewness and kurtosis, right? So how skewed is my data? And so do I have a few outliers or just way beyond what we expect? And then, how does my tail look on that data? And then the distribution of that data. There's many different distributions. So in statistics, the biggest thing is we love the normal distribution, the one that kind of looks like the bell curve, and we can identify where 95% of people will be. But there's a lot of different distributions around binomial distribution and things like that, where we have to take that into consideration if our data doesn't look normal. And then this is where you do a lot of that data visualization, some of the plots against the data. And the reason we do a lot of this is this might actually give you some insight into some questions you may have not thought about with your data or the problem that you're trying to solve. So once you start doing some data visualizations, you might see some things that just look a little bit different. And you're like, okay, maybe I should reform my question. Maybe I'm not asking the right question, or maybe there's something here I'm missing. So these steps here in this data exploration gives you a lot of insight to your overall data. And then the other thing is you might look at relationships among the different variables. So, the correlation between variables. So one example is there's a high correlation between the level of education and the income someone has. And it's not a one-to-one correlation, obviously, but there just tends to be a high correlation between those 2 variables. So you can make the decision, should I have both of those variables within my data set moving forward, or should I go ahead and drop one of those because one of them is enough to give me the insight that I need for moving forward? And that's where that attribute selection comes in. And then there's always, as you start to learn from your data, you see some of the trends in your data, and you notice some things. You may go back to the data curation step and really look at, okay, is there things here I need to change around my schema, some of the variables, all of that stuff that we really look in that data curation to do some of the data cleansing. So those two go hand in hand, and they're really tied close together. And how do I do my data prep before I go into the machine learning process? Any questions or comments on the data exploration part of this? So I just put up an example of just of a data visualization that I have. So I see a question, can we combine Tableau with machine learning? Yes, you definitely can. So tools like Tableau or Power BI or Cognos or any of these dashboarding tools that give us the data visualization aspect are very key to helping us make machine learning better. And a lot of them integrate into different things like Python and R and stuff like that to help you move from the data visualization piece to the machine learning piece. But they definitely are instrumental, because you want to use tools like Tableau or Power BI or Cognos to learn from your data. And sometimes that gives you insights into the questions you may want to ask and predict from your data or your use case as you move forward. And so here I have a data set, and this is actually a data set that comes from, I can't remember what agency in particular, like what government agency it came from, but this is around air quality control over a large city. And if I'm not mistaken, it was somewhere in Asia. And so this is kind of looking at the different factors around, wind speed, high levels of NO2 or CO, so carbon monoxide, stuff like that. So there's all of these sensors that were placed around the city, and they're collecting all of this data. And then there's different ways to color this data to show whether there was a good air quality or bad air quality. And this is a way for someone that is a subject matter expert within that air quality within that city to start to piece together some things around the data. So for example, like you can see a wind speed that you start to get a little bit more green the higher the wind speed goes, right? So obviously it's moving the air out, the bad air out, and just having fresh air. And then so just a lot of different things that someone might be able to pick up from this that works in this type of field. But overall, that's where that data visualization can give you some insight onto where to ask questions and how to ask questions. All right. So this is where we get into what's called in the field of feature engineering. And as I mentioned before, a feature is just an attribute within the data, our variable, right? And so this can be everything from the transactions of a customer, it could be the customer data itself. So one of the examples that was put up with the screenshot was the customer churn example, right? And that's customer retention, and really looking at what are the factors of why my customer may leave my institution or may leave my business, right? And so the features there can be, the customer experience. It can be the number of times they've called, the number of times they may have said something was out of stock. All of these different attributes that you can collect are features that might help you make a prediction to like customer churn. And the reason that we talk about this as feature engineering, and it's that third part of that data curation, data exploration, and then now you do the feature engineering, is you're looking at it from a point of view of how do I remove the noise within my data? So again, if I have some outliers that are really extreme, how do I have to think of the way that I might handle that data overall. There might be some attributes that we just don't use for different reasons, that maybe they're not a significant correlation or impact to the difference in the model's performance. Maybe we want to remove them because we don't want that attribute to contribute to that model prediction. So something like gender or race, we may want to remove so it doesn't, isn't used as the core of building that model. There's also different things there that you might want to think about ethics. So like zip code a lot of times, or stuff like that, where you might want to remove just to remove that noise. And then, you know, you really want to think about mapping your data into different space to make the model algorithm easier to do. And when we talk about mapping the data into different space, that's when we talk about really doing like some mathematical transformations. The easiest example of this is if I'm using income of like a large city, you know, there's going to be like most people are going to be in a median of you know, the national average, but you're going to have outliers that make way more than the national average, and that can skew your data in a lot of ways. So you might do something called a log algorithm or logarithmic transformation, and that's going to make your data look a little bit normal, right? Because it's, instead of this data being exponentially large, it's going to be it's going to move in a certain line step with how the number grows, right? And so there's a lot of things that you might want to think about there. You sometimes might do like a square root of a number. You might square something. So it's just really looking at, you know, how can I change the dimensionality of my data to help improve my model. And then there's also things to think about with reduction of the number of variables. The reason is there's a cost to having a complex model, whether it's a cost of performance, a cost to the computing resource. So the way to think about this is if I can use the least amount of features to give me the best accurate prediction, that's actually a benefit for me overall. And there's things like principal component analysis that helps you reduce the number of features you may have. The other case for this is there might be times where you have a data set that there's so much data collected that in reality, it's just not to your advantage to use everything. So I had a customer one time that had like 2,000 variables collected into a table. And it's not really, you can use all of those variables, but at a certain point, there's going to be such a minimum return from each variable you add that you really want to reduce that down to some of the core correlations to or impacts to the model itself. So again, I know that was like very high level, you know, dumped a lot of information. So I'll pause again and just see if there's any questions or comments about feature engineering, anything that you may want me to clarify for you as well.
Yeah, I just want to comment. Can you hear me?
Yeah.
Yeah, on feature engineering, it requires a lot of domain expertise. If you need to have a good knowledge of the domain. For example, if you are doing medicine-related machine learning, you need maybe to work with the physicians. So it requires a lot of knowledge of the domain area. That's the challenge part. The good part, the positive side of some of the algorithms is they have a built-in feature to do feature engineering. Mm-hmm. So for example, when you cover later on, I know you're going to cover classification, the J48 or decision tree algorithms, they do also feature engineering. They select the most important attributes or features that should stay in the model. So that's a good, if you can, yes, you can do the feature engineering before you start training the machine. If you don't, some of the algorithm, they do automatic feature engineering while they are training the machine or building the model.
Mm-hmm. Exactly, yeah.
Any question? Dr. Brown, she has a question, so go ahead.
No, I don't have a question. I was asking other people if they had questions. One comment I just wanted to make sure that you all stay logged in, because I know that Dr. Ntembe, he had logged off, and then when he tried to log back in, it pushed him into registering for next week. So please do not log off and log back in. But I see Dr. Williams has a question up now, so I'll let you all read that. Also, my Bob Ross.
No, I was trying to put some pictures in here to get some engagement a little bit. But if you think about it, Bob Ross, when we think about feature engineering, it's really painting the picture of this picture that we're going to move forward into the machine learning. So it's really all of the tools and techniques that you need. And that's what Bob was about, was teaching the tools and techniques of painting. So yeah, just throwing it in there for fun.
Good connection. Good connection.
Right.
I liked your Dora one as well.
Yeah. No, sometimes
Yeah.
you do these presentations quite a bit. You have to make fun of it, and then just kind of try to enjoy it a little bit.
Right. And it helps people remember. So now
Yes.
whenever I see the word feature engineering, I'm going to think of Bob Ross and painting and so forth. So it helps me kind of remember the concept better.
Yeah,
That's
exactly.
great.
Yeah.
Yeah. All right. So it looks like we don't have any more questions. So yeah, I guess you can move forward.
Okay. So the thing I want to spend some time here is, what does the model look like, right? I've been talking about, these machine learning models for quite a while. And so let's really dig into what a model may look like. So the first one I want to really talk about is the decision tree model. And as I said before, this is a classification model. And what we're doing is we're starting with a variable here where we have age. And what it does mathematically is it puts a weight to each age. So we have an example here where if someone's less than 40 or someone's equal to or greater than 40. And then in the background of this model, we would have like a mathematical weight to that, because there might be a difference in value for someone over 40 and someone under 40. And then for someone over 40, the first question we may ask, again, this is a medical use case. And what we're trying to do here is we're trying to predict is what's the probability someone's going to take the medicine that they need to take, right? And so if they're over 40 and they have diabetes, if we say no to that, there's a medium chance that they may take their medicine. If they do have diabetes, there's probably a higher chance, right? And that might just be due to the behavior of someone with diabetes is used to having to monitor something. And so they're going to be cognizant of the medicine that they may need to take that has been prescribed to them, right? But if they're under 40, we have a different way of looking at this. And so if they're under 40, we look at the medication price. So if it's less than 100 or if it's greater than or equal to 100, we might start to look at that. And then there might be a weight versus this. So we're going to break down the $100 cost to less than 10, greater than 10. And we start to look at this. And so this kind of gives some insight in how the decision tree really goes. And it's really, I'm starting with something and it's going to break down these different features into different weights and be able to create this tree of decisions. And based off of the variable coming in, it's going to be able to rapidly go through this and give you a prediction. The next one to the right is the neural network. And again, this is the same concept where we have some inputs coming in about predicting if someone's going to take their medication or not. And so we might have age, weight, and price in this case. And then we're going to have these networks of nodes. So each circle is a node. And it's going to be the same concept. So each one of these nodes will create the same thing we create with decision tree. It's going to create a weight. So it's going to create this mathematical formula to be able to decide, okay, which way does it go throughout this network of nodes. And then the last layer that you have in your network, your neural net, is what we call the output. So all of those decisions and weights will come together to make an output decision on the probability that someone's going to take the medication as we expected. The next one is if we look at it from a linear regression point of view. And so we may have it as a way of, looking at it from a y-axis of from a 0 to 100. What's the probability there? And this isn't necessarily the way that you would do something like this, but I wanted to keep that same theme going across of how someone might look at this. So if we look at it from a regression point of view, you're going to have some coefficients against the weight of the variable. And so we have just a simple plug and play where we can put the age in, we could put the weight, or we could put the medical price in. Based off of the change of weight, the medical price, and the age, we can have a coefficient that is associated with the medication. And then the last one, this is the clustering method. And so this is where you, it doesn't necessarily have the same mathematical weighted model. What it's doing is it's going to create this point of convergence where you can distinguish between the two. So whether someone will take their medicine or won't take their medicine in this case. And so we might have, a lot of these down here, the triangles of maybe no's, and these blue dots of yes, right? And so if we look at it, there's some that obviously go to, that look like they probably should be blue, but they're not, and back and forth. So what you're doing is you're trying to create this point that can easily distinguish the two. And it may be a circle around these, or it can be a shape like an oval around these. And then there'll be what we call the centroid, or so the center of that shape, where most of those points will lie within that circle at the center of this point, right? And so it's really just looking at, so how do I group these different classifications that I'm trying to do, a yes or a no, or something like that, into a representation of how do I divide these individuals up. So,
I just want to comment on the neural network. I know Dr. Alzate asked the deep learning, basically to have multiple hidden layers. So here what you see is the inputs, one layer, the middle layer, and the output layer. So in the deep neural network model, you'll have multiple, more than one, the middle layer, or it's called the hidden layer. So that will make it very complex. The more you have, the more complex it becomes. Also, the more you can represent non-linear relationships.
Mm-hmm.
So that's the power of deep learning models. And the way models are trained is they go backward and digest the error. Is called backward propagation. So you can iterate many times to get the best prediction, and the machine is not going to complain.
Exactly it. Any questions here on models in general, machine learning in general, that anyone may have?
I have a question. This is Latanya Brown. My question, I guess maybe I should have posted on the chat, but that's okay. My question is, could give me a situation when is it better to choose between a decision tree and a neural network? Or can I just use them interchangeably?
There definitely will be considerations that you would make before choosing a model. One might be just the amount of data that I have. So neural nets are definitely much more optimized for a large data set versus a smaller data set, just because of the way these layers work and the weights that they put in the nodes. The other thing sometimes is cost. It's a lot cheaper to run a decision tree than it is a neural net when you're training a model. And that's just in terms of the cost of the computer resources needed to be able to achieve these in the time length and all of that. But really the consideration is what are you trying to predict, and how is it predicted? So is it something you're trying to classify? Is it a continuous variable? So is it house prices that you're trying to predict? And so that really kind of will dictate how you use these models and which models you use. And it's not like for these sets of questions you use this model. It's really a little bit of a research process to understand which one do you choose.
Great, thank you. And I see you have a question from Dr. Fox as well.
Yeah, and so it says, to start a project, do you literally sit down with a pen and paper to chart out the process flow? or just write a program to get started. If the latter is the case, is program very important first step in machine learning. And so I would say a lot of times I do sit down with a whiteboard or a pen and paper, and I tend to work with a lot of teams. So what it is we do something called design thinking, right? And so what we'll do is we'll have these sessions where we just really talk about, okay, what is the goal that we're trying to do? What is the current state that we're in? What's the future state we want to get to? And then really try to tackle that problem. Think about, okay, is this problem of value to us? What's the data that we may need to collect? Things like that. And then we do the starting of the programming from there. I would say I do see a lot of people who do just start with the programming, but again, I think the challenge, the thing that slows them down is they have to always come back and think about, okay, what am I trying to do here? So it is sort of better if you just sit down and really think about, okay, what's the question or hypothesis I'm trying to solve? What are some potential data sets I may need to solve this, and then get going and seeing if that helps with, you know, collecting your data and all of the steps you may need to do to make that successful.
Yeah, let me add also the other side of the question. It says, is programming a very important first step in machine learning? I'm going to say no. As Jamar says, it's your problem. And the data sets or the data you have for addressing the problem, then once you determine the problem requires the use of machine learning, then you proceed to do the machine learning. It doesn't mean all problems require machine learning. That's not the case.
Yeah.
So I think that's very important. But like we use SPSS to analyze data, there are, again, Jamar said it earlier, there are a lot of tools like SPSS, even SPSS data modeler, which allow you to do machine learning or training, building model visually. Waka, we will hopefully next week and also today we'll show you, is a easy tools, a GUI-based, graphic user interface-based tool, just like Excel, like SPSS, which you can use if you know what you're doing. So the most important thing is understanding, well, first, determining whether you need machine learning for the problem. If so, what type of machine learning? Is it supervised, unsupervised, or reinforced? Then if it is supervised, then you have to choose whether it's classification, basically, or regression. I think that's basically. So regression, we all are good at doing regression. So I think the new techniques we need to learn is classification. And for the classification, there are a lot of algorithms that allows you to do classification. So normally in practice, you do it by trial and error. Also, it's a very experimental in nature. When you build a classifier or a classification model, you can build it with decision tree, you can build it with neural network, you can build it with support vector machine or other algorithm and compare, evaluate, then choose whichever techniques gives you the result you want based on cost, accuracy, whether you can explain the result or not. There are a number of factors to consider. Yeah. But machine learning is a very experimental process.
Yes, exactly. Yeah. And, so I see the question, no need to learn programming. I would say yes and no, right? There are, sort of what we kind of call the click and point data scientists. And as Dr. Zindi said that, we use tools like SPSS Modeler or Weka to be able to do like this click and point type of machine learning. As your skills expand, I always recommend, learning some kind of coding like Python or R. Really at this point, Python has become like the de facto, and it just gives you more access to control over your model development. But it's not necessarily needed. But I would say it gives you more access to different libraries and different packages once you start to learn how to code as you move forward. So the question around like, when sitting down with your team, are your team members from different backgrounds or similar discipline backgrounds? I would say for the most part, it's a pretty diverse team. I tend to sit with, technologists and business people. And so it's a mix of different skill sets there where someone might be thinking about this problem from a data point or database point of view. I may be thinking about it from the statistical or the machine learning point of view. And then the business team may be thinking about it from an impact to customers or a way to maybe offer a new service or some kind of efficiency within their operation. So it's better to make sure to have a subject matter expert in what you're trying to solve, and then someone that has the skill set to be able to make that happen for them. So you definitely want a diverse team. So yeah, I can definitely explain the decision tree again. And so the diabetes, this is just a sample model, right? So this kind of comes from a real project I worked on where there was some medication that was needed for individuals to make sure that they were getting a certain quality of life. But there was they found that there was a lot of patients that weren't taking the medicine. And so after kind of doing a lot of the data curation, data visualization step, there was a few things that kind of stuck out. One was this diabetes, right? And that's primarily associated with age. So if someone was older and had diabetes, they were more likely to take their medicine. And then the other was around price. So when someone had to actually pay more for their medication, they were more inclined to take all of the medication that was required versus if it was cheap, they had a psychological belief that it wasn't necessarily as beneficial or necessary for them to take. So that's where you kind of get those interdisciplinary teams that can help you help explain why things were happening here. But the decision tree, what it does is, the age was the biggest key factor here, and there's a weight towards that age. And then there was a weight versus, under 40 or greater than 40. And then if they were over 40, we were looking at whether they had diabetes or not. And then there's a mathematical weight there. And then the same with the medical prices. We're putting weights to the different price points that someone had to pay for that medication. Can we add factors at various levels? I'm not too sure what you mean by that. Can you just expand that out just a little bit?
I think she might mean that, like, okay, with your decision tree, can you add in new factors?
Yes.
Like just say down here with diabetes and so forth?
Yes. So this is a very simple decision tree here, but you can imagine this decision tree can be thousands of branches big. So it can take a lot of different variables into consideration. So one of the things might take into consideration is, is the person insured? It might take into consideration pre-existing medication that are, conditions that the patient may have. So there's really like a lot of these different things. And then what you can do too is group a bunch of these together and average it out. And that's what we call a random forest. So we take a bunch of decision trees that have different weights and we average those out. And then that becomes what we call a forest because we have a bunch of different decision trees helping make the prediction as well. So there's that as well. But to all of these use cases here, there's many features that you can add to help explain your model a little bit or make your model better performing or anything like that.
Yeah, again, the new terminology, feature, variable, factors, all refer to the same thing. Mm-hmm. And machine learning, we prefer to call it attribute or features.
Yeah, exactly it.
How are the probabilities determined by the algorithm or the? I think the answer is by the algorithm.
Correct. So there's the predominant way of determining your probability is going to be from the result of the model itself. So in this decision tree, for example, right, you have a different probability of classifying someone as low, medium, or high. And then there's going to be something for this called area under the ROC curve, which I don't kind of go into, but that's a measure to see how well this model has performed with false positives, false negatives, and all of that. And so that probability is going to come from the model itself. There is sometimes the case where you do something called probability distributions, and that's where you take the probability of a feature itself and you create a distribution based off of that. And there's different techniques there that you can use as well. It's not as common, but it is a way to do it. But for the most part, in a practical application, you're going to get your probabilities from the result of the model itself.
Yeah, I think for classification, in particular for decision tree, it's called accuracy.
Yeah.
So unless we use the Bayesian classification technique, we don't get probability values.
Yeah.
Instead, we get accuracy for each decision.
Exactly it. So, for this slide here, it's more focused. Okay, now I have the model that I want to move forward with. What's the next step? So what do I do with my model? And this is where, again, we're not going to spend too much time, but I just want to introduce you to the concept of thinking about how do I deploy my model? And then there's something, once your model is deployed, meaning you can put new data points to it to get a prediction from that. That's when you do something called scoring or inference. And what it is when you score a model is you're giving this model new data and it's going to give you that prediction. And then from there, you can make a decision. We call it scoring when it's more the traditional machine learning process. And then we call it inference when it's in association with like a neural net or deep learning. And one example of this is so like if you guys have ever signed into a website and it has you do the reCAPTCHA thing, and it's like, okay, select the bus, the pictures with buses, right? And you're clicking on the scores of the buses. So you're doing there's an inference that's taking place there from a human point of view is, okay, I know what a bus looks like, so I'm gonna take a picture. Now, when you turn that into a mathematical point of view is, so if I'm trying to make a prediction of, is this customer going to leave my business or not? So like maybe I have a subscription business like a Netflix, and I'm trying to predict whether someone's going to cancel their subscription or not. I might put a new data set, like a new data about this customer, and then there's going to be a scoring arm inference that's created that will say, okay, there's a high probability this customer might cancel their subscription. And then from there, you can make some kind of decision. Should I offer an extended trial? Should I offer a different pricing for that customer and all of that stuff? So there's things that you can do once you can make a prediction in how you move forward. And then I put this slide together much more as like a summary slide for a lot of the things that we talked about. And so it's really looking at this ingest, this explore and visualize, the data preparation, the training and evaluating models, you're deploying your models, and then going live and predicting with your model. And this isn't a steadfast rule, but I sort of feel like the different roles that you might see in these different processes here, just in case if anyone's interested in participating in machine learning, but maybe they don't want to just be solely a data scientist. Maybe you're more interested in the data side, or you're more interested in the application and production side. So I just wanted to kind of put just some rules of thumbs of the different roles you might see here. But no matter what this life cycle is of the machine learning flow, there's a few things that we want to really think about, right? We want to make sure that we can be platform agnostic in our model development. So meaning we can use Python, we can use R, we can use SPSS. It's just being able to use the best tool possible for doing it. There's this huge trend in the industry, no matter what industry you're in, whether you're financial, distribution, manufacturing, is trying to leverage as much open source technology out there. And you see that even with, TensorFlow from Google is an open source tool to do deep learning. And then there's this need to figure out, so how do I do this in real time? So that way, as my customer is interacting with my platform, for example, I'm able to make these predictions in real time. So maybe I can do an upsell, cross-sell, or I could do a retention bonus or something like that to keep my customer satisfied and keep them on the platform. And then, once we kind of get through that, it's the security, thinking about like, how do I secure my data? How do I make sure that my process is available and reliable? So when my customer is on the platform and I do a prediction, it's going to be available for me to get the result from that. So there's a lot of considerations in this machine learning flow that I really need to be aware of. But I just wanted to kind of put this in a summarized format for the machine learning flow and everything like that. All right. So the next is I want to talk about the machine learning tools that just as a overview, right? So we'll kind of talk about the different tools here and why they might be of use or value depending on the framework that you're trying to accomplish and what your goals are. First is going to be the machine learning languages. And I would say, from my experience, Python and R are probably the two biggest that you'll see in the industry. And now Python has overtaken R. I see that a lot more than anything else. I didn't include SAS on here. So SAS or SAS is a software that's been around for a very long time and is in a lot of the bigger corporations, and sometimes in different, like healthcare for some reason uses a lot of SAS, right? But I just wanted you to be aware of what the two most popular are. Now, when you start talking about things like around robotics and self-driving cars and stuff, a common language that's used for that, and it's not necessarily used for the model part, it's more the model creation part, it's used more for that model embedding into a system, is C++ because of how performant it is. So like Tesla, for example, they use C++ in their self-driving component that they have in their vehicle. So when we go over to the data analysis and visualization tools, there's actually a million tools out there that do data visualization. So I have some that are based off of you program and some that are click and create. So Pandas and Matplotlib. So these are two Python packages that allow you to be able to curate data and then also put data into a visualization. So a simple graph, for example. And then you might use Jupyter Notebooks to help organize those graphs. So Jupyter Notebooks is like an IDE for a lot of data scientists, and I use it fairly often. So you have something in there called a notebook where I can put a lot of data visualizations and just have it on a page that's simple to use. You have Tableau, and then there's a million competitors to Tableau, like Power BI, Cognos. There's a ton out there. These are like the tools you use to create dashboards and different data visualizations. And then Weka as well has, the data analysis, data visualization tools as well. All right. So I have a question here. So I have not tried that program before, so I'm not too familiar with it. I've heard it here and there, but I don't really have too much of an opinion on it. But there's a million tools out here to really use. But for me, it is whatever helps you get the job done is the tool you should use, in my opinion. Latanya.
Yeah. So I think with Alteryx, I think the key part within that, from what I understand, is the data cleaning component. So, Dr. Zenabi, are you familiar with Alteryx? I know it's something new, and people kind of link it with a lot of these other programs we see here.
Yeah, I have downloaded the free version and explored it. It's mainly for data curation, data cleaning, data merging, and preparation. So, yeah, it can fall under, I don't know where in this. But the question I have is, I think Weka is more of a framework. Even you can build a model, and it also has a plugin to do coding with Python and R and Java.
Yeah.
So it's more of a machine learning framework. Actually, its visualization feature is very poor.
Yeah. So I use it more. I've seen it used a lot for data analysis. And so this is just kind of a viewpoint of how to use it. But a lot of these can be interchanged in different realms, right? So like I have this big data tools. There's some other, like you can use Pandas for big data as well. So they're definitely interchangeable. and for how they're classified. My main goal here is just kind of talk about the I would say the most common tools you might see out there. The only exception I don't have on here is SPSS. It is very common, but it's just I see it. I don't see it used as much as in industries as it was once commonly used. I think a lot of people have moved to Python.
That's true. That's true.
So next is the general machine learning frameworks. And what these are just the packages that really help either get your data prepped properly or help you build models themselves. And I just picked a few here. Again, this is an exhaustive list. There's thousands of frameworks out there that you can use. So I just wanted to highlight a few. So example like the scikit-learn. That's a very common Python framework to use to help you build out different models. And then this NLTK, which is the Natural Language Toolkit. This is very common for things around natural language processing and doing something like sentiment analysis. So those are some frameworks that you might experience out in the field and are pretty common. Next is the big data tools. I would say Spark is huge out there. Like I see Spark almost everywhere. And it's an open source machine learning. And you can probably put this as like a framework. You could probably put this as a machine learning language because it has Scala. But really what it is it's almost like a machine learning operating system that allows you to build out your models, allows you to attach to different data sources. It has a bunch of packages and libraries already there. And then I put one here that's another one I've been seeing a lot recently is MemSQL, and it's just it's the same concept as Spark. And what it is it's an in-memory database where I can do a lot of query against my data in memory, so I get this fast performance, and then I could pull that data wherever I need to pull it. The challenge with something like a Spark in like an in-memory data system in general is once like you turn off the system, you lose your data. So a lot of times there's a database attached with where these data go, where the data is actually stored. So you use these more to consume data and do a lot of your processing at a fast pace, and then move it where you need to move it. And then the last thing I wanted to just briefly touch upon is the machine learning frameworks for neural nets and deep learning. So TensorFlow, I've mentioned a few times because it's probably the most common in the field, I would say. The other ones that I really see a lot is PyTorch, which has become more prevalent, Keras, and then I haven't seen too much Caffe anymore, but it definitely was very popular in the beginning when TensorFlow just started. But these top three are very popular in the deep learning neural net frameworks. And then there's, again, like I said, there's a bunch out there that you can go and explore. I just kind of highlighted a few here to just talk about some of the tools, but there is tons. You can use Anaconda for packaging with Python. There's RStudio to help you organize R. Like I said, there's SAS, there's SPSS Modeler. There's just a lot of tools out there. Python, like I said, is the most common. TensorFlow is very common. And then you'll see a lot of the Python libraries that are very common. So, do you have to program to use Spark? For the most part, yes. I would say there's a lot of programming with Spark. There are some tools out there that use UIs for Spark, and it's usually like cloud providers. I think Google and AWS have some simple UIs to like get Spark up and running and organizing the cluster and everything. But in general, I would say that with Spark, you're going to use some coding to either get access to data or to run some of the machine learning packages. You're going to usually call the APIs with some kind of code. I think for SPSS, since that's the one I'm most familiar with, there is plugins for Spark to help make that easier. So you can do the drag and drop. But the vast majority of people I see in the field using Spark do have some kind of coding interaction with it. So I have another question here. It says, in terms of employment opportunities, what would you suggest to our students? Okay, that's a good question. So I did take out a slide. I probably should have kept it in. So at the beginning of this other presentation, I usually have a slide that talks about the need for data scientists in general. And I believe in 2020, there's a shortage of like 220,000 or so data scientists within just the United States in general. And that's projected to grow significantly over the next 4 to 5 years. So when you think about anything around machine learning, I would say that the data scientist or statistician is going to definitely be a desired opportunity. And then the pay for those individuals are very high within the industry right now. I think the average pay for a data scientist is like $130,000, $140,000, depending on the city and things like that. But it's very high for the average data scientist salary. And then with that, it's the supporting roles around data. So like the data engineer is a good opportunity if you're much more into that ingestion side and that data management side. There's a lot of opportunity there. There's some around what we call a data analyst, which is much more like, or the business intelligence analyst, which is more around doing dashboards. I think there's some demand there, but it's definitely not as prevalent as you might see with the data engineer or data scientist. And then the other one that I see a lot is the machine learning engineer, which is the person that is a lot of times really focused around the production and operation of the machine learning model. And those are heavily desired right now. Like I said, there's a huge gap in the ability of someone being able to build a model and then actually put that model into a production, into an application to really use it properly. And then there's things like the application developer that's going to be using it. There's the subject matter experts within the business that might be helping things be data driven. So there's a lot of opportunity right now, especially with anything around data and machine learning. So the next few slides I have are just more showing some examples of some code here of a few things. And then I think I just have a couple slides after that. And then I'll leave it open for questions and comments there. And then correct me if I'm wrong, but I believe these slides will be shared with the students, correct?
Yes, we'll share the slides and any other information you have, as well as we'll edit the video and put it on YouTube.
Okay. So the thing here is I won't spend a lot of time on this, but I just want to just quickly show you some of the examples. So in this example here, what I'm doing is I'm doing that partitioning of the data, like I said, and I'm creating a training data set and a test data set here to get the machine learning model ready to go. So in this example, we've already done the data cleansing, and we're starting to look at how do I do the training of the model. So there's going to be some things here where I partition my data set into these different training and testing, and then in this case, I have a validation data set. So it's important because what you want to do is you want to train your model with the data there. So you might use 70 or 80% of that data to train, and it's arbitrary how much of the original data set used to train the model. And then you're going to test against a portion of that data. And then the testing will help do some optimization to the model. And then you'll do a validation. So that's going to be the last test that you do to just determine your accuracy, your false positive, your false negative rates, things like that. So I have that in there twice by accident. So the next thing that we might do is we might do some optimization or parameter optimization here. And so I'm using a package here that what it does is it's going to be able to test against a couple of different models to see which one is performing the best. And then whatever one is performing the best, it goes through what we call the pipeline. And the pipeline is just as I do my data set, I split my data sets and I start to build my model. There's this pipeline that we just say that is happening right with the data. The box right here on top, this is actually some of the feature engineering here, and it's a simple feature engineering. This is where I'm creating some dummy variables, and I'm creating the state here where like it's across the 50 states. And so I'm creating a mathematical representation for each state. So if it's California, I'll have a designation for California. And then this last part here is what we call the vector. So this vector is really just all of the features that I want to go into the model is I'm just classifying these here, and that way the machine will be able to move forward with my features. And then the last part I wanted just to show is, we went ahead and trained this model, and it's a very simple model that we built. So with some fictional data, but what I wanted to do is you want to focus on, okay, how do I save my model? So there's some code here, but the biggest thing I wanted to focus on was actually around this model accuracy. And so this is just a representation, and this is what it's called the area under the ROC curve. So the more this looks like a square, the better. And so what it's saying is that I'm pretty accurate at this data set, meaning I'm accurately predicting, positive when it should be positive, and I'm accurately predicting a negative when it should be negative. So it's just a couple of things I just wanted to show very briefly. This is all, I believe this is in Scala, so it's a very easy programming language to read, pretty functional. So that was the end of the presentation. So what I'll do is we have probably about 15 minutes or so. So I do want to just pause. I know it's a lot of information today. It's pretty long. And, I was a Robert E. McNair Scholar and a Ronald E. McNair Scholar in college as well. And so I remember being in these sessions of learning about how to do research, learning about the difference between qualitative and quantitative, and how to do your problem and hypothesis, and what a lit review is. So I know that during these presentations, there's just a lot of information that can be dropped onto you. So I just definitely want to pause and just take any questions or comments that you may have for clarification, and be able to make sure that this information will help you be successful in your research project over the summer.
Great. Do we have any questions? That's so interesting that you were a McNair Scholar. Yeah. So this program is very, very similar to that, where the students are undergoing undergraduate research. And so did that really kind of help you as far as move forward on different opportunities, as opposed to other people who may not have been these scholars doing undergraduate research?
Yeah, it definitely helped out a lot. It actually helped me get my first job as a statistician at the Cancer Center, because I was able to kind of talk about the research that I did as a McNair Scholar. And I'd have to pull it up. It's been many years since I did it, but I know I did something around statistics and mathematics, and how that impacts different communities, right, with numbers and stuff like that. So it really helped there. And then the other thing I really helped with doing, I did 2 undergraduate research experience. So one was at McNair, the other one was another program. And both of them really helped me get into grad school. So that's how I kind of ended up at Syracuse, is with the research experience I had as an undergrad. It provided a huge scholarship to go to Syracuse. And that's kind of what led me going back to grad school and things like that. So it definitely was very valuable in doing this.
Great. So I see we have a question about will the PowerPoints be available at Blackboard? Yes, I'll put the PowerPoints as well as the video on Blackboard, and any material that comes with this session as well as this session next week. And Dr. Assalti, he wants to know, do you have any other advice you want to offer to our students?
Sure. So there's 2 things I'll kind of offer as advice. I'll make it particular to the machine learning, and then just overall. So my first advice when you're thinking about research and your thinking about machine learning, and if this is an interest to you, is just the hands-on experience. Try to be involved as many projects as you can, where you can learn and experience from it. The second piece of advice I would just give is being professional. And just, I work a lot with our new college hires, is don't be afraid to ask a lot of questions, right? So I do a lot of mentoring with our what we call summit hires. Before I came to Polyblock, that's what I did at IBM. Is I worked with a lot of these young professional hires, and one of the things I saw is that there wasn't a lot of questions being asked. It was more, okay, I'll go, I'll be kind of silent when I'm not sure of something. But in my opinion, for me, the way I've been very successful is I've asked a lot of questions. And even when there's times where I felt like maybe this is a dumb question, it's actually worked out in my favor of asking the question, because it sparked a conversation that no one else had sparked in the room or something like that. So those are like the two, I guess, off the top of my head I would think about, is really just get in there and dig in and get the experience and always learn, and then ask a lot of questions just in general as you continue to move forward.
Great. Thank you so much. Jamar, this has been a wonderful presentation, and I definitely have learned a lot, and it's been very interactive and entertaining as well. Before we conclude, I want to pull Dr. Zenabi in. Dr. Zenabi, do you want to make some announcements about next week and the webinar?
Okay, yeah. First, I would like to thank Jamar for his excellent preparation and presentation. Again, his advice to the students, he's not only saying it, but he's also doing it. So I think for our students, and well, let me focus on our students. Let me leave the faculty alone now. For our students, I think they need to be putting time, and also don't be afraid to try the different tools. Nothing happened to the computer, nothing will happen to you. So the only way you can develop skill and ability is not by watching video or YouTube only, but you have to do it by trying and by doing it. So that's the only way you can break into the industry. I think that's critical, by being bold and by trying and learning, developing skill. Next week, we will try to focus on more hands-on. Jamar, as you saw, he's the Python guru, and he's gonna do different demos using Python. I will also do the same thing using Waka. So we'll give you a couple of examples. Hopefully the technology will collaborate to do live demo. If not, we'll prepare a PDF and show you the step-by-step things that happens and the outcomes. So I think I have already shared two things. One is to use Waka. Please download that on your personal computer, or we have a virtual computer lab at Bowie State University. So I have provided the connection, I mean the URL, and as well as the step-by-step instruction. So try that one, be ready. If you have any problem in either downloading Waka and installing it on your computer, let us know before Thursday. Or if you have any problem on accessing the virtual computer, and within that workstation accessing Waka. Also, I think, what else do we have? Anything you wanna, Jamar?
Yeah, so I would say for next week, what I'll do is I'll do a little bit deeper dive on deep learning and neural nets, just to kind of give some context there, because again, that's where a lot of the industry is moving towards, and there's a lot of reasons why people are moving towards that. And then we'll do the hands-on, and I'll try to send some stuff out by Tuesday next week, so that way if the students need to do anything, they'll have that available to them. And then I just want to thank you guys for the time. You know, I think it's a privilege to be asked to kind of do something like this, especially at Bowie State. One of our employees at Polyblock is a Bowie State alum as well. And so he was thrilled when I told him that I was doing this. So I just want to thank you guys again for the opportunity. And then feel free to reach out to me. My email is pretty simple. It's just jamar@polyblock.io. And so if there's any more questions or anything like that that you have after this that you can think of, just ping me. And, I usually get back to people within a day or two. So yeah, thank you guys again.
Yes, thank you so much, Jamar. And feel free to come into our classes or do whatever. You're like we're going to make you an honorary faculty member at Bowie State University.
All right, sounds good to me.
And I just shared, if you all are still listening, it's just, if you see a red dot under files, if you click on that, you'll see some of the files that Dr. Zenabi has loaded up there for you all to download. And I'll try to get Samantha to send them out to you all as well. And Jamar, if you have any files that you want to share us ahead of time, you can send it to me, and we'll be sure to get them out to the students and the faculty.
Okay. Sounds good.
All right.
Yeah,
Great.
Let me try to share the Weka file. Will I be able to do it? Let me see. Share.
Yeah, I just shared it. Everybody. It says it's sharing. So
Okay.
Yeah.
Okay.
Yeah.
All right.
All right. Well, great. Thank you so much, Dr. Zenabi and Jamar. Thank you so much as well. And we look forward to seeing you guys next week.
All right, sounds good. Thank you, everyone.
All right. Thanks. Bye-bye.
Bye.
Thank you.